Hello, this is another chemical engineering video, and in this one we're going to be talking about mole and mass fractions, which are both important concepts in chemical engineering and chemical processes. So we're going to be talking about what they are and how can they be useful, or how can they be interpreted in a given chemical engineering problem. And we're going to start by defining them. We're going to begin with the mole fraction, which is pretty much given by Y, and it expresses how many moles of substance A can be found in a mixture with a total number of moles of the stream. For instance, if we have a stream flowing into a unit process, a stream with n moles, the molar fraction of A gives us how many of these moles correspond to the substance A. So given a molar fraction of A, we can determine how many moles of A are actually present in the stream of interest. For instance, if we have 100 moles as an input stream for the process unit, and we're giving a molar fraction of A equal to, say, 0.6, then we can isolate for this quantity over here in order to determine how many moles of A are present in the stream. That is, the number of moles of A is the product of the total number of moles within the stream multiplied by the molar fraction of the substance of interest. In this case, we have that 60 moles of A are flowing in the stream. Okay, that's very useful because we can now determine that if it's a mixture with two substances, then the remaining fraction should correspond to another substance. For instance, in an air mixture, if we know that we have a specific amount of nitrogen and oxygen, given the molar fraction of nitrogen, and knowing that it's pure air, we can deduce that the remaining fraction of the unit will correspond to oxygen or nitrogen. And the same happens with mass fractions. If we're talking about a mass fraction of an referred to as X of A, this determines how many grams, kilograms, whatever unit you were working with. Let's say just mass in the mass of the mixture. And the same process has to be done if we want to determine how many grams or kilograms of A are present in the mixture whenever we have the molar, well, the mass fraction of the component as well as the total mass of the mixture. And we're going to work with an example over here. Okay. In this problem, we're given that dry air is made up of 21% by volume oxygen and 79% by volume nitrogen. And we're asked to determine the mole and mass fractions of oxygen and nitrogen in the moist air. Okay, so we're going to revise another concept here, which is the equivalences of mole and volume fractions. And we're going to have to use the ideal Gauss law equation. Here we're given a volume fraction, which we're going to denote by BF of oxygen. It's made of 21% oxygen, or pretty much 0.21 oxygen. And we know that the volume fraction that corresponds to nitrogen is equivalent to 0.79. And we need to establish what the mole fraction of both gases are in moist air. So we're going to take the ideal gas law equation, and we're going to see that the relation between volume and moles, quantity, and the moles within the gas mixture is proportional, which means that as the amount of volume rises, the amount of moles of the gas also rises. That allows us to establish that the molar fraction is equivalent to the volume fraction. In other words, we have that the molar fraction of A is equal to the volume fraction of the same component. So this is now pretty easy to establish, to solve for the first part of the problem. We're going to take this and establish that if the molar fraction is equivalent to the volume fraction, then the molar fraction of oxygen is equivalent to the volume fraction of oxygen, which has already been established to be 21% or 0.21, and the same goes to nitrogen. So the volume fraction of nitrogen is 0.79. And that's how we solve for the first part of the problem. Now, we are also asked to determine the mass fraction of both gases, and that's a little bit trickier, but there's still a way to solve it. And we're going to have to use the molar masses of both gases. We know that the molar mass of nitrogen is 28. I'm going to round that up to integers for simplification purposes, and in the case of oxygen, we have a molar mass of 32. Okay, so in this case, we're going to use what it is known a basis for calculation, and we're going to assume that we're working with 1 mole of substance of moist air in this case. And given this, we're going to determine the mass of 1 mole of moist air given the molecular weights, which we know that are described in grams per mole or grams per gram mole. And also we're going to determine the molecular weight of each of the components, such that given the molecular weight of oxygen within the mixture and the weight of the mixture itself, we're going to be able to determine the mass fraction of oxygen and nitrogen. And we're going to begin with determining the molar weight of the whole substance, moist air. And there are 2 ways that we can go about. And we're going to go through the easy route first and just determine that if there is 1 mole of air, and we know that the molar fractions, then there's going to be 0.21 moles of oxygen, and 0.79 moles of nitrogen. So this let us establish that the mass is equivalent to the moles of oxygen times the molecular weight of oxygen plus the number of moles of nitrogen times nitrogen's molecular weight. This is how we determine the mass of the moist air in grams. So this gives us 0.21 times the molar mass. Well, let's have the units for the dimensional analysis, and we have 0.21 moles and 32 grams per mole plus 0.79 moles for nitrogen, and we have a molecular weight of 28 grams per mole. So we're going to determine the mass of moist air by performing these products and additions, which are 6.72 for oxygen plus 0.79 times 28, which gives us a total mass for moist air, 1 mole of moist air of 28.84 grams. Moles cancel out with moles, and we're simply left with grams. So this is the mass of moist air, and we are required to calculate the mass fractions. So we need to determine the mass of oxygen within the mixture as well as the mass of nitrogen. And we've already calculated them because we were required to do so to determine how many grams of moist air are present in 1 mole of the substance. So we simply determine that the mass fraction of oxygen is equivalent to its mass within the mixture, which is the amount of moles within the mixture times its molecular weight. This is mole, and this is going to be grams per mole. And down here, we're going to plug in the mass of moist air. We're left with a molar, or I mean a mass fraction of 0.21 times 32, which is 6.72, divided by the total mass, which gives us an approximate mass fraction of oxygen of 0.23. Do the same we did the same with nitrogen, or there's another way to do so. We're going to cross that bridge when we come to it. So we have 0.79 moles of nitrogen. Molecular weight of nitrogen is 28 grams per mole. And the mass of moist air, which is it's pretty much 0.77 if we round up. But let's just perform calculation. Yeah, it's 0.766, which is pretty much 0.77. Like I previously expressed, if we know 1 molar or mass fraction, we can determine the other simply by subtracting it from the unit, because the fraction is how many moles or grams of a substance are present per unit of the substance. And so if we have that 0.23 grams of oxygen are present in each gram of moist air, then we can determine that the remaining fraction of the unit is going to be the nitrogen. So the nitrogen is equivalent to this, which pretty much is the same fraction that we calculated previously over here. And that would be it. That's the mass fraction and the molar fractions for nitrogen and oxygen in moist air, given their volume fractions.